All right, everybody. Hello. I know looks like really most people are tuning in via YouTube, and so that, or not via YouTube, but Zoom, which is fine. But if you did want to tune in via YouTube, if it's easier for you or whatever, that's fine. So I'll be live streaming for the next 2 weeks there as well, concurrently. So the Zoom lecture will appear on Canvas, but that does it takes a little bit to process, and then I have to remember to go in and individually click publish. So if you don't want to wait on that process, and with me, depending on me to remember to hit publish, the lecture should automatically populate to Canvas under the Thermo 2 playlist. So there's my disclaimer of all the ways you can access this stuff. So welcome. My name is Regina Vrickus. I think I know most of the names that I see, so that's awesome. If you don't know what to call me, it's Vrickus Vroom, like a car, Vroom. So you can call me Dr. Regina, Dr. Vrickus, Professor Regina, some sort of something like that. I just ask that you don't call me Miss Vrickus because I don't want to. I don't want to feel like a kindergarten teacher, and I got utmost respect to kindergarten teachers. It's not a slam at them. It's just right. We have a dynamic of adult and adult-ish. I'm talking about myself with the ish part. I do have a couple of derpy animals. I've got my dog Leela, who's named after Leela from Futurama. I also have a couple of derpy cats. One's more derpy than the other. So the gray one is glorious, but also very derpy. So the gray one is Joey Softballs. So I guess, sort of my husband likes to nickname most of the animals some sort of mafia name. I don't know why. I married into an Italian family, so there you go. And then Nox, as in Harry Potter, Lumos, Nox, yeah. And then I also have a couple of kids. I won't call them derpy, but a couple of kids. So my daughter is Lily. She's in 2nd grade. And then I have a son, Joshua, who is in middle school. Whew, don't envy that. Anyway, so it looks like everybody that is here has already found the Canvas page, so awesome. So you can access the lectures for the next 2 weeks on Zoom or YouTube, and then the office hours are also on Zoom. And I'm just planning on having them Monday, Wednesday, Friday, 10 to 2, basically kind of between the classes that I'm teaching. So, or not 10 to 2, but 10 to 12. And so there should be on the home page, there is that office hours is a clickable link, so you should be able to get that. So let's kind of go through all the stuff there. So syllabus, pretty cut and dry there, but it's important. It's got my office hours on there as well as where my office hours are on a normal basis. So after these 2 weeks are over, hopefully we'll all be back in person, or we'll still be, I don't know, attending class in our pajamas. But after the 2 weeks, I believe we'll be back, and I'll be in Duke 354. The grading distribution, I've got 6 tests and a final exam. So I've decided normally I have 5 tests in Thermo 2, but I decided to just add an extra one. I think we'll have time, so we will see. I've sort of tried to update the notes so we could progress a little bit quickly. If you took Thermo 1 with me, you know how I sort of run the class. So ideally, you'll go to YouTube. There'll be a Thermo 1 or Thermo 2 playlist, and there'll be videos that you can watch before class. So today we're going to be covering videos 1.1, 1.2, and I think 1.3. So on a regular basis, you would have already watched those videos, but I am under no illusions that everybody has come in and, before the semester started and watched those videos. So we'll go through them in a little bit more detail today, but on a regular basis, I'll kind of go through them rather quickly. But you do need to watch the videos because that's where your derivations come from. That's where your more theoretical concepts come from. And that way we can progress very quickly because we only have these 50-minute lectures, which really, they go by very, very quickly. I don't give makeup exams. We're going to have 6 exams. I won't have any homework. I'll have practice exams that you can take, but I won't have any graded homework. It's all going to be tests. So 6 exams and 1 final exam. And those 6 exams are worth 80% of your grade. I'm going to take the highest 5 grades. I don't give makeup exams because with so many tests, it becomes just a scheduling nightmare. So what I do instead is I drop one of those tests. So if you are sick or something like that, you have to miss a test because of that, that's fine. That's going to be your drop test. If you're never sick, if you just, you have that sort of next couple of months, if you're never sick, I just drop the lowest test grade. I think that's as far as just I think that's the most reasonable way to go about it. So that's what we're doing. Going back to that home page, up at the very top, you'll see there's a embedded Google document. That's where I'm going to put any corrections or anything like that I have. So if I screw something up, shocking, I know, it never happens. It does happen. So if I make a calculation error or I write down something incorrectly, then I'll just put a correction up there, and that way I'm not inundating you with lots of emails, because like you, I get lots of emails and sometimes I'm so done. I don't want any more emails, and I become desensitized to emails. And if something really important comes in, I might just kind of not even see it or not even register that it's there. There is also a link for the equation sheet and the tables and the problem statements, which are sort of guided notes that we're going to go over. Same thing as if you had me before, same kind of deal. The equation sheet and tables, it's a pretty big PDF. It's about 100 pages. You do not need to print it out if you do not want to. You can if you'd like, but as long as you have access to it as you're going over problems, ideally you'd have access to it during class so you can look up properties as well, look at the equation sheet. That's good. I will provide you with that printed out PDF for tests, so you don't have to worry about bringing those things in. If you go to assignments, you'll see how everything's sort of laid out, and on your view, it for some reason defaults to organizing everything by date. I mean, I see why they do it, but if you click by type, it's nice and organized and pretty. So all the tests are at the top, then you get a final exam, and then you've got ungraded assignments at the bottom. And like I said, I don't have homework assignments just because of the grading burden, and we don't pay our graders enough as it is, and we really do ask a lot of them. So if I am really giving the work that they're actually getting paid for, I really can't ask them to do homework and 6 regular tests and a final exam, right? So I don't have homework, but I do have these ungraded practice exams, and the way that it'll go is it'll be just kind of examples, a couple of examples that are similar to what you might be asked on the test, a couple of conceptual questions, a couple of write it out questions, and then you'll be given the final answers after you hit submit. So once again, not graded, it's just for you to gauge how well you are prepared for the exam. Testing is going to be done in person. I had such a horrible time last semester with academic integrity violations, specifically with Thermo 1. Not so much with Thermo 2, but definitely with Thermo 1, and that was because I was doing testing online, and no matter what parameters I seemed to put in place, it was an issue, and it was a continuing issue. So I can't do that anymore. So the flexibility of giving you extra time or letting you take it over a range of a week, that's done. Just show up for the exam. It's all going to be done in person. So what you need to take is just a piece of paper, not a piece of paper, something to write with, and a cheapo calculator. So there is a link on the syllabus for the calculators that are allowed on the FE exam, and that's what you're allowed. So cheapo calculator, no graphing capabilities, no programming capabilities, cheap calculator. That's all you need. I would say, get one that you could have some parentheses in there just because, but yeah. So the way that we're going to do it is you'll have your, you'll come in, you do your test like normal, and when you turn it in, you'll give me the hard copy, but while you're at my desk, you will also scan in your work, with your phone and upload it to Canvas. So for exam 1, you're gonna scan your work and you'll upload it to exam 1, upload and submission. And this way I have a hard copy, but I also have a digital copy that I can give to my graders immediately, so hopefully they get feedback faster. I have a digital copy that no matter where I am, right, I can access your test. So if you have a question and I've gone home for the day, well, I can pull up your test wherever I am and I can, you know, answer questions or whatever the case may be. So I think that will be a nice kind of good organizational tool. You have to give me the hard copy though, okay? So both of those things have to be done, but the hard copy I gots to have, because if I just have a digital copy, but I have no proof that you were actually solving it in the room, then there's nothing to prevent you from sharing it with somebody in India and saying, hey, solve this problem for me. Here's my login information. Upload it for me. Thanks. No, got to give me the hard copy as well. So anyway, we'll go over that as well, you know, another time just so you got it. But there you go. Probably a good idea to do a trial run. Make sure that you can scan a PDF and upload it to Canvas. So you need to download a scanner app and you need to download the Canvas app. So both of those things. Doesn't have to be Adobe Scan. I just like Adobe Scan. You can use whatever scanner app that you want to use. That's fine. Just make sure that it all works before you show up for the exam. Okay. Everybody good? Everybody have questions? If you have questions, just interrupt me. It's fine. I won't be upset. There's a link to the YouTube channel and it'll bring you to the Thermo 2 playlist. This lecture will populate on that Unit 1 playlist after class, so that will be there as well. And then as far as, you know, I mentioned that ideally you would watch videos before you come into class. That way it's not the first time you've been exposed to it and we can go it through quickly. If you're wondering what videos to watch when, if you click on the class schedule, there should be kind of help you, you know, a guide about what you should watch when. Obviously, you know, I mean, this is with some sort of flexibility because we're going to progress how we progress, and there you go. The only thing that I'm not going to that I would not be super flexible about is the exam dates, because people plan things around that, right? I plan things about if I absolutely have to be somewhere, well, I'm going to be planning, you know, my schedule around it, and I know that you do too. So those exam dates, you know, unless there's some sort of huge thing outside of our control, some act of God, then we're keeping the exam dates the way that they are. Nick asked, will the test be similar to Thermo 1, 5 multiple choice and 2 short answer? It will most likely be 5 multiple choice questions and 1 short answer, because we have 50 minutes and the experience that I have, especially with Thermo 2, the problems are kind of involved and they take a while. And so, you know, one problem might take you 50 minutes. Okay. But like I said, we're going to have 6 regular tests and a final exam. Final exam would have 2 or 3 problems on there. Okay. Anything else? We're good? Maybe we're good. All right, so let's go ahead and get to our lecture. So if you look at those guided notes, oh my goodness, look at those. They've got a makeover. They have clickable links in there. Amazing. So I did that last week. I was pretty proud of myself. I'm sure there's some errors there. Some sort of link goes somewhere else, but you know, hopefully everything's good. All right, so ideal cycles, this is video 1.1. As far as, yeah, so we're going to be talking about power cycles. And actually, I'm going to zoom in to this corner over here because we're going to be talking about cycles. And we're going to be talking about ideal cycles. Yeah. We're going to be talking about power cycles as well as heat pump and refrigeration cycles, and just kind of remind you of what you might have covered in Thermo 1. we analyze these power cycles as sort of black boxes, right? So that box right there, there's my black box. Got a little counterclockwise, or not counterclockwise, clockwise arrow indicating that it's a power cycle. And a power cycle works by pulling heat out of this high temperature reservoir. There's my Q dot N or Q dot H, and then it dumps some waste heat over here to our low temperature reservoir. That's our Q dot out or Q dot L. And then we have a W dot, and this is a net out. Net out. So any W dot out minus W dot M. If you need a review on that, if you look on the second page of these notes, right there and there, those are your review videos for power cycles and what those are. All right, but a power cycle, that's what it does. In Thermo 2, we're going to look at what actually goes on in that black box. Okay, and we have a set of assumptions that we're going to typically use for these cycles, and it's not just power cycles, and it's not just gas power cycles, which is what Unit 1 is about. So ideal cycle assumptions, we've got a couple of them. One is that all of the processes are what we call internally reversible. Yes, so Jack asked, are these going to be recorded and uploaded for review? Yes, yes. But stay here. This is going to be super exciting until 1:15. Yeah, no, 2:15. Oh, it's 1:25. Oh my goodness. Okay. Yes, 2:15. Yes. So all processes are internally reversible, meaning the big one is that you don't have any friction. Big one. So all processes are internally reversible. The other one is that you don't have any heat transfer, so heat transfer is negligible where unintended. Unintended, yeah. So as far as like deviations that we'll consider, well, think about what this means. So if something is reversible and adiabatic, so let's kind of put that on there. Actually, if a process is reversible and adiabatic. Adiabatic means that there's no heat transfer. Right? So in a cycle, in a power cycle, it doesn't mean that you don't have any heat transfer, right? This assumption right here doesn't mean that you don't have any. It just means that where you don't want it to happen, it doesn't happen, right? So in the connecting piping or something like that, you don't have any heat transfer. In compression and expansion processes, you don't have any heat transfer. So if it is an adiabatic process and it's reversible, it's an isentropic process. Okay. All right. So if you need a review on isentropic stuff, entropy, all that stuff, because if that's sort of screaming back at you now like, ah, crap, it's okay for now. It's okay, but you do need to go back and review. Like this right here would be a big one, a good one to review. So down at the bottom, these are all review videos, like if you need just a refresher, and there should be some clickable links on there as well. But that would be a big one to look at. So deviations from an ideal cycle would be non-isentropic expansion and compression. So when we talk about Brayton cycles, gas turbine engines, we're going to be specifically talking about isentropic efficiency. So you would be talking about an isentropic efficiency for a compressor or a turbine less than 100%. I'll say others here, but the others is something that we won't really talk about in this class. We're going to be just focusing on non-isentropic expansion or compression as far as deviations from that ideal cycle. Now, other things that could deviate from that ideal cycle, other, irreversibilities just in general. So friction, maybe you do have heat transfer where you don't want it to happen. Maybe you do have heat loss in the piping that you would have to account for, but that's not something that we're going to account for in this class. We'll keep it nice and simple. So that's for any cycle that we might analyze. So we'll talk about power cycles and refrigeration cycles in units 1, 2, and 3. So all of that stuff would be applicable. These ideal cycle assumptions would be applicable for those things. We're going to focus on unit 1 and 2 on power cycles, and unit 1 is just going to be gas power cycles. So in a gas power cycle, your working fluid stays as a gas. Okay, so, and we're going to have a special set of assumptions called air standard assumptions that we'll use when we talk about gas power cycles. And it's sort of a subset of these ideal cycle assumptions, and there is some overlap, just so you know. But we've got a couple of these. So number 1 is that your working fluid is air. It behaves as an ideal gas. So ideal gas. So what that means, just stopping right there, it means that your ideal gas law, you need to be able to use that. So think of MRT equals PV, right? That yeah, I should write that. So you have mass, yeah, MRT equals PV, or you could have it in terms of specific volume. If you divide both sides by mass, that would be fine. It also means, just kind of as a side note, if you have an isentropic process and you have an ideal gas, you've got these isentropic relationships. Okay. So let's go see what that looks like. So if you go to the Canvas page, that equation sheet and tables, is there an easy way for you to share the problem set guided in a Word file? I'm unable to type notes on the PDF file from a computer. I'm not sure how to convert the files. Oh, you want to type it? Yeah. Please. Hold on a minute. Do it right now. Try that. See if that gets you the oh, it's probably going to open as a Google Doc now that I think about it. Which actually is fine, I think. Try that. If it's not good, I'll just email you the Word doc. Okay, Adam? So those isentropic relationships, you can find those on your equation sheet. Yeah, absolutely. You can find those on your equation sheet. So in that packet, that big PDF packet, you've got actually two equation sheets. One's the Thermo 1 equation sheet that I've used for my Thermo 1 classes, so it should be familiar with you if you've had me before. And the other one is just for Thermo 2, but you'll have access to both of them. So these are the relationships for ideal gases. This is all chapter 6 of Morin and Shapiro. It's my unit 6 for, you know, the way that I organize Thermo 1. So if you want to review the Thermo, actually 5 and 6, I think, but I think it's, yeah, I think unit 6 is where we talk about isentropic relationships for ideal gas. So you've got some equations that you can use if you assume specific heats are constant, and some that you can use if you don't assume specific heats are constant. So like I said, if you need a review on that, go review. And over here, there's your links for all your review videos if you need. All right. So working fluid is air. It behaves as an ideal gas. Let's see, all processes are reversible, internally reversible. No friction, that's the big one. And then I told you there was a little bit of overlap, and there's your overlap. And then the third one is that your combustion and your exhaust processes are modeled as simple heat addition processes and heat rejection processes. So exhaust would be heat rejection process. So combustion specifically is a pretty complex process, right? You start with say air and your fuel, and you end up with something else. You have a chemical reaction and you end up with something else. And so the way we're going to model combustion is very simple, right? We've got our working fluid, it's air, it undergoes a process, combustion process, and we're modeling that combustion process as just a heat addition process. So your air comes out at some high temperature with more energy associated with it. So once again, if you want to see that a little bit more detail, video 1.1 is where you're looking. Or actually, I'm sorry, video 1.2 is where you're looking. And then there's a fourth assumption that gets added to those air standard assumptions if you make the assumption of cold air standard assumption. And that is you have constant specific heats. And I'll say, unless otherwise specified, we're taking K for air to be 1.4. So this is, you remember, this is the ratio of Cp over Cv, and it's taken at 300 Kelvin. That means that your Cp is 1.005, your Cv is 0.718. Okay, keep on keeping on. 1.3 is all on reciprocating engines, meaning they reciprocate, they go back and forth between two positions, top dead center and bottom dead center. And so we do define this compression ratio, which would be your max volume within your combustion chamber and your minimum. So this is, you can see over here on the left hand side, this is a piston cylinder type arrangement, and this right here is where, that's your combustion chamber, that's where it takes place. And so as that piston head, as that moves down in your diagram, that's your maximum volume. So that would be the volume at bottom dead center. And then the minimum would be when whatever's in that combustion chamber is compressed. So this would be at top dead center. Okay. And you could put that in terms of specific volume as well if you'd like. Okay. Mean effective pressure is another one of these parameters that we use sometimes. So MEP, so it is a fictitious pressure that if it acted on the piston head throughout the entire piston stroke, throughout the I'm sorry, not the piston stroke, the power stroke. If it acted on that piston head throughout the entire power stroke, it would generate the same amount of power as the actual cycle. And it's defined as work net out, and that's a capital W, work net out over the maximum volume minus the minimum volume. So the units on here, you can see it's in kilojoules. If you were in SI units, it might be in kilojoules per meter cubed. So you'd probably need to convert to units of pressure. Right, so kilopascals, bar, PSI, something like that. So just, you know, watch your units there. Okay. Right, so I'm gonna kind of scroll sort of slowly. Like I said, I do have quite a lot of review videos if you need a review on the first law, specifically closed systems, which will be applicable to our AutoCycle and our diesel cycle, which is what we're going to cover first. Stuff for ideal gases, and then open systems, which we'll get to in a couple of lectures. All right, but before we get to the cycles, we'll do just a pretty simple review. So air is compressed in a, no, all my corrections, and I didn't get that one. Darn it. Have to get it next time. All right, air is compressed in a piston cylinder reversibly and adiabatically from 300 Kelvin to 700 Kelvin, and we want to find the compression ratio. So compression ratio R, and we're assuming that air behaves as an ideal gas. In order for us to kind of progress through this material really quickly, you'll see that I've already put out given, find, assumptions. I've already written that out so we can kind of save time there. But on a test, of course, I'm not going to do that for you. I'll give you, here's the problem statement, and then it would be up to you to list the given, find, assumption, solution stuff and fill in that stuff. You need to have all four of those things. That's important. So I would suggest as you study, you know, just like in any engineering class, go back and solve the problems on your own, cold, that you go over in class. So just have your problem statement, cover up the solution, and see if you can solve the problem as well, including what is my given, what's my find, all that stuff. Okay. So we've got air, we're assuming it behaves as an ideal gas, and it's an adiabatic and reversible process. So adiabatic and reversible, adiabatic and reversible both mean that it's an isentropic process. Okay, so we're going to keep that in mind. And then I know my compression ratio, it's the maximum volume over the minimum volume. And we're talking about a compression process. So the maximum volume is going to be before the compression. Minimum volume is going to be after. So this is going to be V1 over V2. And you know, it's air in a piston cylinder assembly, so it's a sealed system, meaning that the mass is constant. And so I'm not going to change this ratio by dividing through the the top and the bottom by the mass. And so that's going to get me things in terms of specific volume. Now the reason that I'm going to do this is because I have this isentropic process, which means I can use an isentropic relationship for ideal gas. All right, so remember that's on your equation sheet. It's on the first page of that equation sheet. Show it to you right now. Nope, just kidding. All right, so this is page 3 of that big PDF packet. And so on the bottom of page 3 is where you're going to find those isentropic relationships for ideal gases. If I don't assume that specific heats are constant, then these are the equations that I can use. And of course, you see that my compression ratio, it's in terms of specific volumes. So I think this one is the one that I'm going to use. All right, now you might be wondering, well, what about the ones on the left-hand side? Because they look a little bit simpler to use. Maybe we can use those. Let's do the ones on the right, and then we'll talk about if we can use the ones on the left. The ones on the left assume that specific heats are constant, so maybe not. Okay, so but for now, let's use this one that I've kind of got boxed in here. Okay, so an isentropic relationship. Now, I have written down directly, I'm going to write down directly from my equation sheet what it says. It says V, I think it says, which order does it say? Okay. It says V2 over V1 is equal to VR2 over VR1. All right. So that's only if we have an isentropic process for an ideal gas, which we do in this case. Now, VR1 and VR2, those are the relative specific volumes, and those are things that you're going to find on your ideal air tables. So where are those ideal air tables? Well, if you don't remember, if you didn't have me before, you know, you don't have an idea of where these are in the packet. Here we go. We got our table of contents there. It's on page 19. So I'm going to go to page 19. Here we go. So this is table A22, page 19 in that packet. And I know that T1, T1 was 300, T2 is 700. So 300 and T2 looks like, here we go, it's 700. So looks like, and here's our VR1, and then our VR2 is that one right there. So I'm just going to pull that stuff right off the table and throw that in my equation. Okay, so I have, this one is, oops, I'm sorry, yep, 69.76. This is 621.2, but of course I'm interested in V1 over V2, not VR, or not V2 over V1. And so, of course, this becomes 621.2 over 69.76, and I end up getting 8.9. Now, I did mention that, okay, well, what if we did make the assumption that specific heats are constant? You may recall from Thermo 1 that, you know, if you're not talking about a big temperature difference, one on the order of like a couple of thousand degrees, but maybe you're only talking about a couple of hundred degrees, which is definitely the case here, making the assumption that your specific heats are relatively constant is an okay thing to do. It's not going to lead to a great amount of error, right? You can have some amount of error, but you know, a small amount of error might be okay with you. So let's put it like that. If we assumed specific heats are constant, since our delta T is small being on the order of a couple of hundred, not a couple of thousand degrees temperature difference. We'll take our take those CP, CV, and the ratio of those two things at the average temperature. Okay, so our average temperature in this case, so we're looking between 300 and 700, so that'd be 500, right? 500 Kelvin. And if you look in table A20, we can get whatever value that we want. Okay, but we're going to use our isentropic relationship, where we assume specific heats are constant. And I think we can use either, all three of those are valid, but I think this second one is going to be the one that we need, because we're interested in the ratio of those specific volumes. We know the temperature. We're going to be able to figure out the K value. So let's use that one. Let me look at that again. Is it switched? Yes, it is. So T2 over T1 is equal to V1 over V2 to the K minus 1. And at 500 Kelvin, let's go look at what our K value would be. So table A20 has, let's go get A20. There we go. So ideal gas, specific heats of some common gases. We've got air, we're looking at 500 Kelvin, and our K value would be 1.387. So this is table A20, 1.387. .387. So I'll bet, plug in that K is equal to 1.387 and solve for V1 over V2. It will be very close to 8.9. The first way that we solved it is a lot, so the first way is a lot more accurate, but the second way is, if you're not talking about a huge temperature difference, it's probably okay. Depends on how accurate that you need to be. Sorry, guys. For those of you who were paying attention, I guess. Just, all right. All right. Thanks, David. All right, so let's look at the first law review. So closed system, this is going to be where we're talking about our Otto and our diesel cycle. And then for our open system, we're going to be talking, that's going to be used for our Brayton cycle or our gas turbine cycle. In Thermo 1, we use sign convention, but in Thermo 2, when we're talking about cycles, we're going to be talking about, we're going to be using subscript convention. I'm sorry, I'm all thrown off now. Okay. So subscript convention, instead of just using Q or W and using a positive or a negative sign to indicate whether energy is going into or out of the system, we're going to use a subscript, and that Q in and Q out, W in, W out, all that is going to be a positive number. So the first law in subscript convention and sign convention, they're both given on your equation sheets. You don't have to memorize it, although after writing it down a gajillion times, you probably will memorize it. Okay, so for the first cycles that we're going to talk about is going to be closed system analysis. All right, we got 10 minutes, so we're going to introduce this idea of the Otto gas power cycle. So AutoCycle is what we're going to be using to to model that the gas turbine or gas power cycle, so gasoline engine. So this is a spark ignition engine. The actual cycle, and I have some nice little nice little videos that I stole from somewhere on video 1.4, although I think I gave them credit. I hope I gave them credit. But some awesome animations that somebody did. So you've got the actual cycle consists of, you've got a piston cylinder arrangement, you've got two valves, you got an intake and an exhaust. So what comes into the intake valve, through the intake valve into that piston cylinder, is fuel and air, and then it's compressed to a high temperature and pressure. Then the thing that initiates that combustion process is the spark. You got a spark plug, and then that combustion process forces that piston head down. Then when it comes back up, your products of combustion go out with the exhaust. So that one is, the actual cycle. It's not actually a thermodynamic cycle, because a thermodynamic cycle would be, you've got the same working fluid, and it undergoes a cycle so that the initial state and the final state are exactly the same. That's not really what's going on, but we're going to model it with a thermodynamic cycle. So it's a very simple model of the internal combustion of a gasoline internal combustion engine. There are other models, but this one is the most simple one. There are going to be 4 processes. I would caution you against trying to tie each of those processes, right? 1, 2, 3, 4, trying to tie it to these 4 processes right there, because it doesn't map exactly. It doesn't map perfectly, just so you know. All right, so in our special model, our AutoCycle, we have 1 to 2. This is an isentropic compression. Okay. 2 to 3 is a constant pressure, constant volume heat addition process. 3 to 4 is an isentropic expansion process. And 4 to back to 1 is a constant volume heat rejection process. So from 2 to 3, that's where we're modeling our combustion process, and 4 to 1, we're modeling our exhaust process. All right, so let's apply. What in the world did I do? Oh, you, Regina, what in the world? I've got my first law for an open system here. That won't do. That won't do at all. Like that. All right, here's what we're gonna do. Mark this out. Can't believe I did that. So we're modeling this as a closed system. So what I'm going to do is I am going to apply my first law here. And I know we're out of time, but for a closed system, it's going to be Q in minus Q out. All right, you know what? It's 2:09. We'll stop there. Yeah. All right. So the next time that we meet, we will derive these equations, but if you want to kind of get ahead, go ahead and watch the video on the AutoCycle. So video 1.4, we'll work a problem. The next time that we meet, we probably won't progress. We'll probably work that problem and then start to talk about the diesel engine. So make sure that you watch. I would say go ahead and watch up to video 1.5, and that way you'll be safe, okay? Okay. All right. How did the tables work when we take? Okay. So yeah, Casey asked how did the tables work when we take the test in person? I'll bring it. Yeah, I'll print them out and I'll have a little booklet that you could borrow for the test, and then you'll hand it back to me so you don't have to print them out or anything like that. Okay. All right. Thank you guys. Appreciate it. Sorry. Yeah, it's one of those days, I guess. All right. Thank you very much. I will see you guys next time, okay? Thank you.